In this tutorial, we'll be discussing isotopes and the atomic mass. All atoms of a given element have the same number of protons, which once again, that's the atomic number. They do not necessarily have the same number of neutrons. Atoms with the same number of protons but different number of neutrons are called isotopes. All elements have their own unique percent natural abundance of these isotopes. For instance, if we're looking at neon, naturally occurring neon contains 3 different isotopes. Neon 20 with 10 protons and 10 neutrons, neon 22 with 10 protons and 12 neutrons, and neon 21 with 10 protons and 11 neutrons. Notice that every single one of them have the same number of protons, but they have different numbers of neutrons. Remember that the number of protons is the atomic number, and the atomic number indicates what element it is. So in order for it to keep becoming neon, it has to maintain those 10 protons. Once those 10 protons change, then the element that it's represented changes. The neutrons, however, can be different, and that changes the weight of the nucleus, the weight of the atom itself. And that's what an isotope really is. Isotopes are often symbolized in this way with a chemical symbol, and then the atomic number, which is the number of protons on the bottom left, and the mass number, which is the protons and the neutrons added together on the upper left. So if we looked at these, neon 20, 21, and 22, each of them would have the symbol Ne for neon. Each of them would have 10 on the bottom left because they all have 10 protons. By definition, neon has 10 protons. This 20 here represents the mass number. So neon 20 would look like this, neon 21 would look like this, and neon 22 would look like this. Knowing that this is the protons and the neutrons added together. So that means this one has 10 neutrons, this one has 11 neutrons, and this one has 12 neutrons. Another way to depict the isotope is with a chemical symbol or the name with a hyphen and the mass number after it. Remember, the mass number once again is the protons and the neutrons added together. So neon-20, neon-21, neon-22. Or you can write out the word. The atomic mass of each element is listed in the periodic table, represents the average of the mass of the atoms that compose the elements. So the average of the isotopes. And it takes into account the relative abundance of these isotopes. So normally in traditional algebra that you've done in the past, you would ordinarily take 20 plus 21 plus 22 and then divided it by 3 because there's 3 of them. We don't do this in chemistry. We take the natural abundance, so we take this percentage here into account, the 90.48%, 9.25%, and 0.27%. We take that into account when calculating the atomic mass because we want the atomic mass to be closest to whatever isotope is the most abundant. So, since there's 90.48% of neon 20, 9.25% of neon 22, and 0.27% of neon 21. What we're going to do is change this percentage into a decimal by moving it over 2 spots. So 0.9048, and then multiplying by that mass, by the atomic mass of that isotope. I move the decimal place over twice, so 0.0925 times the mass number, or AMUs, the mass of that isotope. Move it over twice, 0.0027 times the mass of that isotope. multiply these three numbers individually, and then add them together. And that's how you get the number on the periodic table. There are two numbers you typically see on the periodic table. One is the atomic number, which is the number of protons. The other one is the atomic mass, which is the average of all the isotopes added together. Here's another example. This should say chlorine. So, if 75.77% of chlorine is chlorine 35, notice that they give you a more exact mass. I was using the mass number here. This actually has the more exact mass of that isotope. If that number is given to you, use that number instead of the mass number. So 34.97 times 0.7577. Chlorine 37 has a mass of 36.97 AMUs, and it's 24% abundant. So 0.2423 times 36.97. Multiply these up individually and then add them together, and that's how you get 35.45 AMU on the periodic table. Notice that since there's more of the chlorine 35, the number is closer to 35. Notice here, since the number is closest to 20, the final answer is going to be closest to 20 because of the fact that it's most abundant. And that's what we're trying to do with the natural abundance. So in general, the atomic mass is calculated according to the following equation. You take the fraction of the isotope times the mass of that isotope. And you do that for every single isotope that's available for that element. So the fractions of the isotopes are the percent of the natural abundance converted to their decimal value. So divided by 100, you move the decimal place over twice. Let's do another example of this. Gallium has two naturally occurring isotopes, gallium-69 and gallium-71. Gallium-69 has a mass of 68.9256 AMU and a natural abundance of 60.11%. I want to take this percentage and I want to convert it over to a decimal, so 0.6011 by moving the decimal place over twice, times 68.9256. Notice when the AMUs were actually given to me, I used that number rather than the 69 number. I multiply that together to get 41.43. Gallium-71 has a mass of 70.9247 AMU and a natural abundance of 39.89. So 0.3989. I took the percentage and divided it by 100 and moved the decimal place over twice. That's how I got that number, times 70.9247. Once again, because the AMUs were given to me, I used that number instead of the mass number. If that AMU is not given to you, you can use that 71. It is very close, it's just not as exact. I multiply that together to get 28.29. I now add these two numbers together to get 69.72 AMUs. Notice that our two options are 69 and 71 for the isotopes. Because there's more of the gallium-69 in natural abundance, the actual answer is going to be closer to it. The nuclei of some isotopes of a given element are not stable. These atoms emit a few energetic subatomic particles from their nuclei and change into different isotopes of different elements. The emitted subatomic particles are called nuclear radiation. The isotopes that emit them are termed radioactive. Nuclear radiation can be harmful to humans and other living organisms because the energetic particles interact with and damage biological molecules. Some isotopes, such as lead-185, emit significant amounts of radiation only for very short periods of time. Other isotopes, like plutonium-239, remain radioactive for a long time, such as thousands, millions, or even billions of years. Radioactive isotopes are not always harmful, even though sometimes they are. Many have beneficial uses. Specifically, a lot of them are used for medical purposes. Technetium-99 is often given to patients to diagnose disease. The radiation emitted by this isotope helps doctors image internal organs and detect infection. And that is how you determine the atomic mass of elements.